Okay, good morning. Let's start. So first, you all have the hard drives. I left a few right here. So if you blow one in the middle of the night, you can rush here and take one from here. And I'll bring some more next week because I have lots of them. So there will be enough here. There's plenty of them. But remember, there are several sitting inside here. Okay, so the assignment is posted on the web. All what you have to do is take it apart, which is the biggest challenge because it has these teeny Torx screws, you know, the star-shaped screws. So you go to mechanical engineering workshops, they have the screwdriver for that, or I'm sure your labs may have it too. And the other thing you need is a power supply. So you go to any lab which has a power supply, preferably a big power supply, like maybe tens of volts and a few amps, because you have to do all kinds of tests there with demagnetization limit and so on. So once you manage to open the drive and connect two wires to the coil, as you see in the assignment, you have to do a plot of force versus current in arbitrary units, which is very simple. You have to estimate the steady state limit on current, and you have to estimate the demagnetization limit. Both estimates are done empirically. So when I say estimate, it's not do calculations, because you wouldn't be able to calculate it anyway. It's tricky, but I mean estimate empirically. Okay? So basically you have to think a little bit about it. If somebody gives you an actuator and you know nothing about this actuator, how do you estimate empirically what is the demagnetization limit and what is the steady state limit? Okay, good. So I'm down. I sold them all out. Okay, so there are none here. Forget what I said before. But I'll bring some more next week, just in case you blew your drive testing. Okay, deadline on this is 3 weeks from now. Okay, it shouldn't take more than one evening to do it. So is that okay, or do you have any big exams or something coming up?
What's the date?
27th of March is the deadline. So I don't expect you to have any urgent thing to do between now and the 27th. Okay, and after that there will be just one more assignment, and that completes all the assignments in the course. The last assignment will simply be a dry run on the exam. So I'll give you an exam which looks like the exam you'll get, I think, on the 23rd or whenever the date is of the exam, just so you can practice and know what to expect. And this will be 10% of this last thing will also be treated as an assignment, 10% of the mark, and that's it. And after that you are free people. So, good. So, to go back to today's subject, I just want to summarize a bit actuators, and we start talking about motors today. So, okay, so to summarize actuators, we covered briefly piezo actuators. And piezo are not useful in micro machine devices or MEMS because it's hard to produce a lithographic process in piezo. But piezo are very useful in miniature. So when I talk about actuators, there are MEMS, which are very, very tiny and typically electrostatic. There are normal size actuators like motors, stepper motors, things like this. But there is also a range in between, which is miniature actuators, but not MEMS. For example, actuators which are the size 1 centimeter or half a centimeter. And piezo is very good for those, because piezo is basically a monolithic block. You don't need gears, you don't need slides, you just take a block, come out with two wires, and you have an actuator. So that's very appealing. What's not appealing about it, when you put a voltage on this block, you can barely see it move, because I mentioned before, the strain on piezo is only 0.1% of L. Okay, so if L is the length of the piezo, and you put a voltage on it, it will only change at the most 0.1%, which means to get a 1 millimeter movement in piezo, the piezo has to be a meter long. Okay, so that's the problem with piezo. Now, there is something which looks like a fix, but it really isn't. The fix is called a bimorph, and I mentioned it last time. You put together two layers of piezo, one which shrinks with the voltage, let's say, and one which expands and one which shrinks with the voltage. So when you connect the voltage in the right polarity, so you tie all these two together and you tie this together, this will expand, this will shrink, and you'll get bending, which is much more than this 0.1%. Okay? But this is still not very useful. Can somebody guess? Because this seems to amplify the movement by as much as you want. Because mathematically, if you make it as thin as you want, you can amplify by infinity. So what's wrong with that? Why aren't all piezo actuators made like that? Can somebody think of it? That's a purely mechanical engineering problem. It has nothing to do with understanding piezo. Yes?
It's also flexible?
It's also what?
Flexible?
It's soft, yeah. The stiffness is very low, because if you push against it, if this was infinitely thin, an infinite strain will develop in the material and immediately squeeze it back to flat, or infinite stress, right? So basically, there's one disk drive short. Okay, I handed out disk drives, you'll get it next week. There's an assignment posted. Okay, so the thing with this, that the same way it moves a lot, it's also soft. The analogy of this versus this is simply the analogy of a mechanical lever. If you take a mechanical lever and you put an actuator here you get a small movement but big force. Here you get a huge movement but little force. But you can't get both. You can't configure an actuator to get big movement and big force. Okay, and the reason you can't, because it's a lever. The bigger you make the movement, the bigger the force, and the force will just squeeze the actuator itself. Because the actuator itself, like a piezo block, also acts as a spring. So if you squeeze it with a force of F, it will actually change dimension. Okay? Just like a spring. So although it looks like a rigid block, even a rigid steel block, if you make a huge enough lever, you can squeeze it. So piezo is much less rigid than steel. So it can't generate a force bigger than the compressibility of the material itself. Imagine you made an actuator out of rubber. You can magnify it as much as you want, but if you pull here, the rubber will compress. Right? So because piezo has such small movements, it's very easy to compress the block. So that's the downside of piezo. So it looks, when you are not familiar with it, it looks like the miracle actuator. All that it is, a block with two wires. You can get big movement if you want. But when you start working with it, you realize it's pretty useless, because you can only get very small motions. You cannot drive it fast, because it will appear you will be able to drive it at megahertz, because it's just two wires. But you realize, as I mentioned before, that these things have a huge capacitance, because the epsilon r can be as high as 100,000. So they have huge capacitance. If you want to drive them very fast, you need very high currents, and they get hot. So you can't drive them fast anyway, even if you had such a power supply, because they get hot. Now let's see if somebody listened well Tuesday. Why would they get hot? Because a capacitor doesn't waste energy. If you drive a capacitor with a sine wave back and forth, it doesn't get hot. So why would a piezo actuator get hot if you drove it with high frequency, high voltage? Okay, that's a good test to see who listened. No, come on. When you take a piezo actuator through a sine wave, it doesn't just go following the sine wave, big and small. It does something else. What does it do? Hysteresis. Very good. So the piezo does something like this. When you run it through a sine wave, it does something like this, just like a magnetic actuator. So I explained when we talked about magnetism that this area, if you calculate, actually represents units of work. Okay? and I wouldn't get into the proof right now, but the area of the hysteresis loop is the energy lost per cycle. Okay, both in magnetic circuits and in piezo. So if you take this thing and you make it go through this loop very fast, each cycle is going to waste this energy and it'll get very hot. So in reality, piezo has very small movements. The movement cannot be magnified much because you lose stiffness. So this is okay for say a buzzer, like I showed you last Tuesday, a membrane which flexes to make a noise because the stress is low. But it's not okay for a real actuator. So the movement cannot be magnified without losing stiffness. You cannot run it at very high frequencies, although it appears you could, because the capacitance is huge and it has hysteresis. So altogether it has quite a limited range of uses, which boils down to things between 1 millimeter and 10 millimeters. Or 20, and that's a whole. You wouldn't find a piezo actuator this big, and you wouldn't find a piezo actuator micro machined, right? It's the niche it fits. It's just a certain size range where things work out about right. Something to remember that it shrinks proportional to E, the electric field, which is measured in volt per meter. Okay, so if you have a big block, it will need many thousands of volts, which is very inconvenient, especially if you want thousands of volts at high frequency. So there is a standard trick, which I mentioned Tuesday. How do you avoid the use of such a big voltage if you have a big piezo? And that trick is what? Stack them, yeah. You stack many layers, so and you put them in parallel. Okay, that's piezo now. Everything I said about piezo is also true about another type of actuator called magnetostrictive, and this is less familiar because I know all of you heard of piezo and maybe used it in the lab, but there is exactly a dual actuator to piezo called magnetostrictive. And it has all the advantages and disadvantages of piezo. Now I mentioned when you take a piece of magnetic material, you put a coil around it, that magnetic material will shrink a little bit when it's magnetized. That's called magnetostriction. And why does it shrink? Why does it change dimension as the magnetic field changes? Realignment. Very good. Realignment of domains. Domains are physical boundaries which slide and rotate, and because of this it changes sizes. Imagine a box full of stones, irregular stones, and you're trying to rotate the stones. As you rotate the stones, they don't fit in the same box. You know, the dimension changes. So that's magnetostriction. Exactly the same story as piezo. 0.1% L, or L, like this, small l, 0.1% L maximum strain, okay? Good thing about it, it's easier to make in big sizes, because you can easily make a big rod. There are special alloys developed to have maximum magnetostriction, the same way as there are special materials developed for maximum piezo. The best known material for piezo is called PZT, and this P stands for lead, the Latin for lead, Z stands for zirconia, T stands for tantalate. So that's lead, zirconia, tantalate, PZT. Everybody refers to it to PZT. Piezo was discovered first in quartz or some other materials which are very low coefficient. But the best piezo material and the most common is PZT. Maybe not the best, but the most common. Okay, same thing here. Every magnetic material has a bit of magnetostriction. I gave you the example that you walk by transformers, you can hear their humming, okay? And what materials are transformers made of? What magnetic material is a transformer made of? Pardon? No, that's high frequency transformers. That's true too, but big power transformers, the ones you hear making a hum on the road, at the street, what are they made of? You have to say 4% silicon steel. I mentioned that because the steel with the best hysteresis loop, which is cheapest, is steel with 4% silicon, and that was a big breakthrough because that's about 10 times better than regular steel. And they're also laminated. Why are they laminated?
To make the magnetic flux.
Pardon?
It's to help the flux go through the core better.
How does it help the flux to go through the core? What problem does it avoid if you laminate the core?
Eddy current?
Eddy currents. Because if not, there is a shorting turn. You should know that from first year. If you make a coil around something, there will be a current because it looks like a transformer. It's like a transformer with a shorted secondary. So if it's laminated, you cannot have a current loop going through the core, like in a short circuit, right? Anyway, you should know that. I know this has nothing to do with the course, but you really shouldn't be allowed to graduate if you don't know that. Okay? So back to this. So the same as piezo, any material has magnetostriction. You can develop special materials which have the best magnetostriction, and the best one developed is called terphenol D. And for those of you who like to know the source of names, there are many miracle materials which have the ending NOL. Okay? For example, nitinol. Nitinol is a miracle material where all medical instruments are made of. Do you know what nitinol is? It's something which is 10 times more springy than steel, 10 times more elastic. So everything in medical is made of nitinol because you can fold it to a very small thing, put it in the body, and it jumps back up to full size. Okay? So there are some materials which have the ending NOL, like nitinol, terphenol, and somebody knows where this ending comes from, NOL. Now that you wouldn't know. NOL stands for National Ordnance Laboratory. It's actually a US Navy lab in Maryland which did fantastic work on materials. And they invented nitinol, invented terphenol, invented many materials. And all their materials have the name, they named them NOL. This is just, this terphenol is just terbium, ferrum, NOL. Yeah, I think so. Okay, anyway, so all what you have to remember is that there is a magic material called terphenol D, which is the best magnetostrictive material there is. So if you want to make a magnetostrictive actuator, don't start with steel, don't start with silicon steel, just buy yourself a rod of terphenol, because it has a magnetostrictive coefficient maybe 100 times better than normal materials. Nickel, regular nickel is also not bad. Before terphenol, people used just regular nickel, because nickel is magnetic and has a big coefficient. Now, this thing is actually much more useful than piezo in industry, although I've never seen a student who actually heard of it. And the reason why it's useful, because that's how ultrasonic drills are made. There is all kinds of processes which rely on ultrasonics, like to weld, to drill, and all these actually have this actuator rather than piezo, because it has to be big. It has to be high forces, actually it's about this big. So this is a bit too big for piezo. Piezo is only for little things. One reason is piezo becomes fragile. The Piezo material is very brittle. It's like a ceramic. So if you make a long stack, it's very brittle, delicate. It can debond. The bond between the layers can open. This is a solid piece of steel. It's much more rugged. Like typically in a drill, this is like a 1-inch rod of steel. So this is actually used quite a lot in industry. And the third type of actuator, and with this we can wrap up actuators, which is a often forgotten actuator, but a very simple one. If you need something which moves very little, but doesn't have to be fast at all, okay, you can just take a piece of metal and put a heating coil on it, okay, and heat it up, and then it becomes longer. And you can use this as an actuator. So this is good and bad. What's good about it is that you can pick a metal which is quite stiff. So the actuator can have very high forces. Okay? And it's also very cheap. You can get it any size you want. You just put a heater on it. Of course, it's part of a servo loop, so you don't really need to know the temperature. You just push it until the servo says you reach set point. Okay? So that's actually a very simple, very cheap actuator. It has a slow response time. This can respond in microseconds, this can respond in microseconds, this needs many seconds to respond. But it's a very, very simple actuator, and until recently, until maybe 20 years ago, it was used in every car made in the world. Now let's see if somebody knows where this was used in every car in the world. And maybe still used in some, maybe still used in cars, but I'm not sure if it may be still used today in cars, but I'm not sure. But for sure, up to say 10-20 years ago, every car in the world had this actuator of this type. Can somebody guess where it was in a car? Yes?
Thermostat?
Pardon?
The thermostat?
No, thermostat is bimetal. Thermostat doesn't have a heater. Thermostat in a car is a just bimetal disc, which just does this, but it's pure bimetal, just like the thermostat here, inside the building, wherever it is there. But the thermostat is also a heat-based actuator. But where was it used in the car?
This isn't the thing that makes the cigarette lighter pop out, is it?
It is, but it's a bimetal. Again, the cigarette lighter pops out by bimetal.
Okay.
So, but I'm talking about not a bimetal. I'm talking a pure linear actuator, a rotary actuator, which is based on expansion, not a bimetal. Bimetal is a different type of actuator. It's also heat responding, right?
Great.
But no, I'm talking about a pure, something you heat up and changes lengths.
The choke?
Pardon?
Or activating and deactivating the choke?
Choke, I'm not sure. It is a bimetal as well. Choke is a coil, at least in the old cars. Let's put it like this. In the days where I used to fix my own car, which was a long time ago, the choke was a bimetal coil. Okay? Yes?
It's in the cooling fan, bimetallic strip.
In the cooling tank?
In cooling fin in front of the cooling fan.
No, that's again a bimetal. All the examples you gave are bimetal. The choke, the thermostat on the coolant, the cigarette lighter, these are all bimetals. They are brass and steel welded together, and they bend. But I'm talking about an actuator which expands linearly by heat. You're getting it's getting warmer and warmer. Where is the instrument panel?
Actually, in the fuel tank in the
Great. How did you know that? Took one apart?
Yeah.
Yeah, good. Okay, so the fuel gauge in all the cars works like this. You have what you have is you have a pointer. Here it says empty, here it says full. And there is a piece of wire. There is a piece of wire with a spring wound around this. So if you pass a current through the wire gets longer, and as the wire gets longer, the pointer rotates. In this or maybe it's wound the other way, it doesn't matter, but the current determines how long the wire is, and this determines what the fuel tank gauge shows you. The other end of this wire is connected to a slider inside your fuel tank, which has a float. So if this is your fuel, the float will float, move on the slider, change the current, and your fuel gauge will follow it. Okay? So that's how fuel gauges work. So this is the most common example of a simple thermal actuator. You just change the temperature, it changes lengths, and then you have an actuator. It's actually a very robust, very simple actuator. That is the reason, by the way, when you fill up a car, the fuel gauge doesn't respond instantly. When you fill up the car and put the keys back, the fuel gauge doesn't jump to full. It goes up quite slowly to full. The reason it's quite slowly because these actuators are slow. It takes a few seconds because maybe you didn't notice it, but when you fill up a car and you start it again, it takes a few seconds for the fuel gauge to go up. Okay? Because the thermal actuator. Okay, so I think that you can keep reading about these things. There are many exotic and clever actuators. Yes?
Didn't they replace the switch? You said that this was...
Pardon? No, I said I haven't fixed my car for years, so I don't know. I don't know if they still use it, but I noticed on my car it still goes up slowly when you put in the keys. So most likely it's still this actuator. But you know, the cars now, they like to put a microprocessor in every place where you don't need one. So this could be replaced by a million lines of code. so I don't know what they do in cars, but I suspect it's still the same just by looking at the response of the fuel gauge, that it's slow. Okay. So this kind of simple and good actuator, I used it myself many times to stabilize optics. Like if you have an optical mirror and you want to stabilize it to a huge tolerance, like you have to have the laser beam hit some place to 1 microradian tolerance. So you really want an actuator which is very stiff, because you don't want to pick up vibrations or anything. So one good way to do it is you put the mirror on 2 bars, and one of them you heat. One of them you heat, so you can tilt the mirror by a teeny amount, but it's a very stiff mount. Vibrations wouldn't affect it. Okay? So this actually, because these things drift very slowly. If you're trying to fix drift in optical systems, the drift is very slow, so you don't need a fast actuator. The drift comes from the whole system misaligning, but it just has to respond in hours, not even in minutes. Okay. Good. So. Yes?
Does it have a name?
No, because nobody heard of it. So it doesn't mean but it's basically thermal expansion actuator. There were some very clever devices used on thermal expansion actuator. There were some very clever thermostat based on the fact that some materials, when they change state, they change volume a lot. Like water, say when water becomes ice, it expands 10% or something. So this actually, if you want an actuator to work around 1 temperature and to change a lot, there's very clever ideas. People use naphthalene, which is a moth repellent, as an actuator, and all kinds of things, because some materials change state a lot at the temperature when they go from liquid to solid. So some very clever actuators based on that, because there's a lot of force generated. Think if you wanted a thermostat to control something to 0 degree, exactly to 0 degree. All what you need is a block of ice and a micro switch. At 0 degree, it expands and shuts off the switch. Right? If it goes above 0, it melts and the switch turns the cooling on. Okay, so there's a lot of actuators like that, simple actuators based on expansion. But in terms of classic actuators, I think we spent enough time on those. Okay, so now, I mean, the rest is all up to you. If you're interested, you have to read up, because this is the whole course is, I think, something like 14 lectures or something, so it's really not enough time to cover this. Okay, so now we move on to the next subject, which is motors. And motors are the same as actuators, but they can go continuously. Now, motors don't have to be rotary. Motors can be linear. But the difference when you say motor or actuator, when you say motor, you mean something can go on continuously. Doesn't reach the end and stop. For example, the rapid transit in Vancouver is a linear motor. But we call it a motor, not an actuator, because it can go on and on and on, right? So there's many motors which are linear, although most motors are rotary. But basically, you can take any one of the actuators we discussed and do some trick to turn them into a motor. In other words, to give them infinite motion, infinite range. So I'll give you one example. The trick they convert piezo actuators to motors is quite elegant. Let's say you want a piezo actuator which, instead of moving 0.1 L, can move unlimited amount. So the original trick to do that was very nice. What you do is you had a shaft, okay, and you put a sleeve of piezo on it. Okay, so this is piezo material. Okay, and you put some ring of piezo, so some ring of piezo here, and some ring of piezo here. And what you did, you made this move the same way a worm moves on the ground. You gripped this end, and you shrunk the tube. So basically, if you put a voltage here, that tube shrunk. So you gripped one end with this ring and shrunk the tube. Now the tube became shorter. Now you gripped this end and let this end go. Okay, so now this moved forward. Okay? And now you repeat the operation. So each time you do that, it steps 0.1 L, where this is L. So if this is L, okay, I'm not sure if everybody understood what I explained. Okay, let's say if this is a rod and my hands are the grippers. Okay, so first you grip the rod. Now what you do, you release one end and you shrink the tube which connects the two rings. So you shrink the tube, it goes like this. Now you grip this and you let this go and you let the tube expand. Then you grip this, let this go, shrink the tube, so it keeps walking, okay? Exactly like a worm progresses, and that's why this is called an inchworm actuator. Inchworm actuator. So that was the original continuous piezo motor. Of course, you can also build it rotary, that it goes around. Later on, the more popular one today works a bit different. The more popular one today, you have a block of piezo, and by having two sets of electrodes, you set up some kind of elliptic motion. So instead of making the block vibrate like this or vibrate like this, you actuate both faces of the block at the same time to generate an elliptic motion. And because it's an elliptic motion, it will have different friction in this way than this way. Because in one direction, it presses. So if you have an elliptic motion of a point, in one direction, the point will press down to the rod. In the other direction, it will release the pressure. So if you have something, if you do some kind of an elliptic motion, it will tend to go forward. Just watch my hand, right? If this is a rod and this is a piezo, and I do this, it's always pulling on the bottom and going forward. Okay? And this type of actuator was popularized by an Israeli company called Nanomotion. And that is quite popular today when you have long sliders and you want a piezo motor to travel back and forth. It can't travel very fast because remember, if this is, say, a centimeter, it can only move 10 micron per cycle. And it can only move, I don't know, a few kilohertz per second. So altogether it can only move maybe at the most a centimeter per second, or in that order. So it can't move as fast as a linear electromagnetic actuator, but it's very precise because you can do one cycle at a time. And each cycle moves at about a nanometer. Okay, because they don't use the full potential, they actually use very small voltages, so each cycle is only a few nanometers. So you can creep with nanometer accuracy. Okay, so this is an example how you can convert an actuator to a motor. Now the same thing was done with magnetostriction, and you can do the same thing with thermal. You can do, you can use every linear actuator can be converted to a motor. The simplest way to think about it, think of a ratchet. If you have a ratchet wheel, basically you have a ratchet wheel like this, okay, and you have a linear actuator with a pole, okay, something which catches the ratchet. Let's draw it maybe like this. Let's draw it here. You have a linear actuator, and the linear actuator has something like this with a hinge. Each time the linear actuator will go up and down, the gear will move one tooth. Okay? So obviously, if you have a linear actuator, you can convert it to a motor, but the trick is how to do it in a more elegant way without actually having a wheel with teeth. So this piezo elliptical motion is equivalent of an invisible ratchet. And there is similar magnetostrictive motor, so the idea is to make it with an invisible ratchet. Okay? By the way, to reverse it here, you just reverse the connection and the ellipse is the other way. You just reverse the shape of the ellipse, it goes the other way. So one class of motors is just actuators which were converted with a mechanism similar to a ratchet. Okay? But that's not how most motors work. So what we are going to cover starting today is how do most motors work, like big motors. Because these ideas, as you can see, are not suitable for big motors. Because at the end, they rely on friction. So at the end, if you push very hard, it will just slide back. Because the whole thing relies on pure friction. That's what's holding it. Okay? And they also have eventually some wear, although they can design it well, that they don't. So what about normal motors like your hand drill or your fridge or your electric car? How do they work? So, I'm not talking about steam engines or things like this. I'm talking about motors used as actuators. So the first motor which was useful as an actuator and as a motor, of course, was the original DC motor. So when we talk about motors, as you'll see in the next few lectures, there is really only three types of motors, if you want to generalize. One type of motor, like the DC motor, is based on commutation. So I'll explain in detail what it means, but if I talk in general about electric motors, there's motors based on commutation. Then there's motors based on rotating field. And I'll explain all these terms in the coming lecture, so it doesn't matter if you don't know what they are now. And there are motors based, all kind of esoteric motors based on these ideas of ratcheting. Okay, so basically, let's just call it. And this is only for very small, for miniature. So this is only for miniature devices. Okay? So there is no name for this class, but there's a whole group of clever tricks how to make actuators into motors or miniature devices. But in terms of really motors which can do useful work, big motors, there's only two classes. It's only these two. Where you see these is in little piezo micrometer control, piezo adjusters. For example, there is a company which makes little instruments called New Focus. And they make an adjustment screw which looks like a normal adjustment screw, but they put around it a miniature piezo motor, and it has a wire coming out, so you can use this screw like a normal knurled screw. But if the adjustment is in a place which is not accessible, you can send it a signal and the screw will turn by itself. So that's quite an elegant implementation. The thing is not much bigger than a normal screw. Right? A normal screw is maybe 10 millimeter by 20, and this is maybe 12 millimeter. And it has a very, very thin flat cable, and you can network a bunch of them. So you have a machine with 100 adjustments. This is designed to be networked as a bus, and you can address each one. So it's all designed very nicely to be compatible with a computer. So you can control all these screws in inaccessible places. So this is a good example of this ratcheting piezo motor. But this, as I said, this whole range of exotic motors is only for anything between maybe 1 millimeter and a few centimeters, just in this scale. Anything else has to be this or this. Okay, so what is commutation? Or maybe before I explain commutation, let's talk a little bit about the history. Who built the first electric motor? Faraday. So I told you the rule. If you don't know, say Faraday, you're 50% right. Okay. So Faraday thought a long time about how to make an electric motor, and he came up with a motor which is beautiful conceptually but completely useless. Okay, so he thought of the problem that if you take a conductor, if you have a magnetic field, so this is a magnetic field, and Faraday understood magnetic fields already in conductors, and if you put the whole loop in the magnetic field, there is no net force. Right? The loop will rotate, but after it rotated 90 degrees, nothing happens. If you put one conductor in the magnetic field and the rest of the loop outside, the conductor will move. So there's going to be a force. The conductor will move until it gets out of the magnetic field, and then it will stop. So either way, you will not get continuous motion. If you do it by a loop, you'll get maximum 90%, or maybe 180 if you flip it over. If you do it by a single conductor, it will move until it ends the magnetic field. So Faraday was thinking how to make it go forever. So it's very difficult to make an infinite magnetic field. But Faraday had a better idea. He said you can make an infinite conductor. That the conductor, when this comes out, a new conductor comes in, so the conductor is always in the magnetic field. Okay? So what he did is something very, very clever. He took a magnet, and I'll draw it in 3D. So he took a magnet like this. These are the poles of the magnet. Say this is N, this is S. Now he put a copper disc. He put a copper disc which is going through the poles of the magnet, and he put an electric contact here and another electric contact here. So now current is going this way through the magnetic field. This is a magnetic field. Current is going through the magnetic field, so there is a force on this current. Basically, there is a force on the disk. But as the disk rotates, there is always a new conductor to go into the magnetic field. Okay? Is that clear? So this way, there is always a conductor in the magnetic field, and it always rotates. And this is called Faraday's homopolar motor. Homopolar motor. It's beautifully elegant, but it has one problem that you saw in all the examples before. We increase the magnetic field, or we increase the force by putting n terms to get Ni. We always put multiple terms to increase the effect of one term. Here there is only one term, and for 180 years people thought about it, and nobody found a trick how to expand this idea to multiple terms. Okay, I mean, you can make windings here, but then it's not a continuous sliding contact. Then you can need what's called a commutator, which I'll explain. But if you want to have a simple sliding contact, Faraday did it originally with a vat of mercury. So the copper ring was dipping in mercury, and that was a sliding contact. In the old days, everything was done with mercury until it was discovered it's toxic. But in the old days, like in every lab, there were bathtubs full of mercury, and all the equipment was floated in mercury. Everything was done with mercury. So this was done with a pot of mercury, later on replaced by a contact. But because it's only a single-turn motor, N equals 1, so it doesn't have much torque. Okay? But this is about one of the most elegant motors. So this is a replica of Faraday's motor. Okay, so you have the magnet. The black thing is a magnet. At the bottom, the black thing is a magnet. There's a copper disc. There's a contact at the bottom. What I should really do is should get this thing going, and then we can see much better than the next motor as well. Okay. Okay. So we'll wait until this gets going. In the meantime, I'll explain what it does. So I have a battery here. So this motor, obviously, because the conductor is just a short piece of copper, has very low resistance. Because it has very low resistance, obviously it's a motor which needs a very high current and a very low voltage. And that's another problem with this motor, because you cannot change it from one term to many terms. You cannot make it a motor which works on a lower current, higher voltage. Right? Because when you transmit electricity, you want to use higher voltages and lower currents. Why is that? You need thinner wires, because if you transmit a high current, then you need much thicker wires. Okay? So Good. So when I connect this motor to a battery, just like Faraday saw in 1850, okay, what's happening here? No. When I connect this thing to a battery, I think the battery is a bit dead because it barely moves, or maybe it's not a good contact. I think it has a bad spot, so when it turns until it reaches a bad spot, then it loses contact. Okay? So now I'll put it under the document camera, then you can see it better. Okay, so again, this is a copper disc. Okay, at the bottom there is a contact. This is a bottom contact which touches the copper disc. In the middle there is a second contact. So the current is flowing like this. Current is flowing in this area. The black part is a magnet. Okay, so if you put it here and you touch it, it starts rotating. See, and that's what Faraday saw, as I said, around 1850, was very pleased, reported to the Royal Society right away. Okay, but it's not a useful motor. So then people started inventing a better motor, and interestingly, people thought of a generator or dynamo before they thought of a motor. Because at Faraday's time, the only way to make electricity was from batteries. And then batteries run out and don't have much power, so people wanted to make electricity in a different way. And they realized if they take a coil and rotate it in a magnet, it will induce a current. It would be AC, but then you could do some trick, which I'll explain in a minute, called commutation, make it into DC. So people actually built generators much before motors, or what they call dynamos. Usually when you say dynamo, it means DC. And when you say alternator, it means generator for AC. Okay? So like Edison's machines were referred to as dynamos. Okay. So at one point where there were dynamos connected in parallel, the belt of one dynamo broke, and people noticed the dynamo starts rotating. And then they realized that a dynamo run backwards is a motor. And that's how they started developing motors, and there were many, many people and many steps. So I'll skip all the steps and explain how it works. So the first successful type of motor was a commutating DC motor. So imagine, so first I'll explain it and then I'll demonstrate it. So imagine that you have two poles of a magnet, N and S, and of course they usually are connected to close the magnetic circuit, like this. The field is going this way. Okay, now imagine that you have a loop wound this way. So what you see here, I'm just summarizing as this is the two ends of the loop, okay? And this loop can rotate around the center. So this is the center of rotation, so this loop can basically rotate. A bit like a meter, like an analog meter. Okay, so in 3D, this is the conductors, this is a magnet, okay? And it can rotate. So if you put the loop in this position, say this is this, this is this, the loop will generate its own magnetic field if you put a current into it, and this magnetic field will try to align itself with the main magnetic field, because the loop is the same as putting in a magnet. So if I put here a magnet aligned this way, the magnet will rotate to align itself with this. Right? And we talked about it before when we talked about electromagnetic actuators. So if the loop is this way, it will stop moving, because once the loop is vertical, it doesn't need to align itself anymore. So I'll just draw the sketch here. So if you have a magnetic field B, so if the loop is sitting this way, it generates a magnetic field which is already aligned with the main magnetic field, it doesn't turn. Now if you put the loop at any other orientation, it will generate a magnetic field which will force it to align itself to this position. So if it's this way, it will have to travel 90 degrees and it will stop. Okay? The loop can also be made to travel 180 degrees, because if this magnetic field is this way and you flip the loop over so the magnetic field is this way, it will have to turn 180 degrees to align itself. But you'll never be able to make it go more than 180 degrees. Because if you put the loop at 270 degrees, it will go 90 degrees the other way. Okay? So obviously you need some trick to convince the loop to keep going, and that trick is called commutator. And what people said, and okay, I'll redraw it here so you can see the commutator. What people said, let's put in a switch. Let's put in a switch on the loop, so whenever the loop reaches the position that it doesn't want to rotate anymore, we'll switch the direction of the current so it will keep rotating. So each time the loop wants to get to the point of equilibrium, the switch forces it to keep going. So the way this is done, I'll just redraw the field. Okay, so this was the original loop that I drew. So the way that's done, you put two conducting arcs, they made typically of copper. These are two conductive arcs, and you connect the coil one end to this arc, one end to this arc. Okay? And you put two contacts, which are called brushes, two strips. Okay, so this is called commutator. And these are typically called brushes because in the early motors they actually looked like wire brushes made from metal wire. And another terminology, this is always called in motors a stator, and this is always called the rotor. The part which rotates is called the rotor, regardless of which part is in, which part is out, because you can build a motor reverse, that the rotor is at outside, but the rotating part is always referred to as rotor or sometimes armatures. In older books, or some books, it's referred to as armature. This is called the stator, or sometimes it's referred to as a field. These are all terms dating back to the history of motors. These are called brushes. This is called the commutator. So now let's see what happens if you do that. So if you have a coil, like we described before, so I will leave this drawing here so you can copy it. I'll just make a new drawing on this side. Okay, so this is a magnetic field, and I'll draw it all along the blackboard. B. So let's draw the contraption from there at different stages of rotation. So we start with the loop horizontal, and the commutator looks like this, and the brushes look like this, and they're connected to a battery. So what will happen? The brushes make contact with the battery. The current will flow in the loop, and because the loop is at 90 degrees, or the flux is at 90 degrees to the field, it will start rotating. Okay? So next position, let's say the loop will be like this, brushes will be like this, they are still making contact. It's still rotating. Okay? Okay, now in the drawing, let's draw that it rotates this way. Okay. Now it comes to this position, and at this position, actually what happens, there is no more current because the commutator is actually shorting out the brushes. Okay? So that's a complete short. These two things short out, they short out, there's no current in the loop. Or another way of saying it, the current goes in both directions, so nothing happens. So if there is no current, this will keep rotating out of inertia. Okay? Because once there is no current, it already started rotating. It'll keep rotating out of inertia and get to this position. Now at this position, the contact is established again. But now, if this was the magnetic field before, let's say the magnetic field before was N, okay, and this is N, this is 0. Now at this position, the magnetic field will reverse, because the plus was touching this brush, and now, because it rotated over 90 degrees, the plus is now touching the other brush. Right here it was touching both brushes, here it was, now it's touching the other brush. So this plus is now actually touching this side. Okay? So now the motor will reverse polarity, and now it will have S, because the current reverse polarity, which wants to keep turning it because it's opposed to the field. Okay? So basically what this does, each time it wants to sit still, you rely on inertia to take it a little bit farther, and then it switches the polarity to keep the force in the same direction. Okay? So that's the simplest commutator. You already can see the big problem with it, that if you start up the motor when it was in this position, nothing will happen. If you left the motor in any other position, if you apply voltage, it'll start turning. But if you are unlucky and the motor stopped at this position, you apply the voltage, you can get a short. Okay. So what's the solution to this problem?
A number.
Yeah, have a number which you cannot get a dead spot. So right now we have 2 segments you can get a dead spot. What's the smallest number you cannot get a dead spot? 3. So if instead of 2 you will do it like this, you will have 3 coils, and each one will have a segment, and these coils are connected together. The brushes will always conduct to some of the coils, so it will always start. So the basic electric motor works like this, but instead of 1 coil, it has 3 coils and 3 segments. Okay? So to show you how this works, I just made a flat motor so everybody can see how it works. So you have I'll show you here under the projector. Let's tilt it, you can see better. Hit the lights. Okay. I just can't see very well. So I'll do both. I'll hold it up and then I'll put it on the projector. So it has a rotor with 3 coils. It has a stator with 2 coils. Now the stator can be either a permanent magnet by connecting a DC voltage to the coils, then it becomes magnetized, or it can be used as a series motor, which I'll explain next week. So basically you convert the field into a magnet just by putting DC on it. And the DC goes to the coils, and you have 3 segments in the commutator. So now we can look at it here. Okay, so if you look at the commutator, you see it has 3 segments. So you cannot find a dead spot. Like if I look at it now, it's still connected, it's not shorting. If I turn it a bit, the little lines you see are the gaps. These little lines, just point it out over there. Hold on. Just go in. So what you see there, these lines are the gaps between the segments of the commutator. These are the 2 brushes. So there is never a dead spot where it shorts out, because it's 3 versus 2. Okay, now these coils, which end up here, are connected straight to the battery with these 2 wires, and the commutator is also connected straight to the battery. So these coils just convert the frame into a permanent magnet. So now, if we take a battery, okay, so here I have 3 batteries, so I can give 1.5, 3, or 4.5 volts. Okay, you can see the battery here, the background. So it starts running. Now, it doesn't matter where I stop it, I can move it at any position, it will always start. So that's the whole idea of using 3 instead of 2. Okay? So this is this type of motor It's called a DC motor or a commutating motor. That was the first motor invented, and it's still the most popular motor in the world, surprisingly, for reasons we discuss next week. Okay? Now, the only flavors you can replace these coils by a permanent magnet, because if these coils are always connected to the battery, why do you need to waste power? You can put a permanent magnet. Okay? Or you can do some tricks, which I'll explain in a few minutes, that you can take advantage of these coils in all kinds of clever ways. But the basic motor, or the most simple motor there is called a PMDC, which stands for Permanent Magnet DC. So the simplest motor is called PMDC, standing for Permanent Magnet DC, and all what it is a frame like I showed you, but has two permanent magnets inside. Typically they are rare earth magnets, so typically they are very small. So these are the magnets, and this is N, and this is S, and the field goes like this. Inside it has an armature, a minimum of 3, but you can have more than 3, and a commutator, and brushes. Okay? Now one thing is interesting, when these brushes touch in this position both segments of the commutator, there is really a short. And that's bad, because it will be bad for the battery, bad for the brushes. But even when you have 3, when you don't have a short, you have you straddling between one coil and the other, and you get a lot of sparks. You are changing the current rapidly. So the trick is that if you use simple metal on metal, there will be a lot of sparking. It will eventually erode the metal. So what you want to do is you want to put something here between the metal, which has all the miraculous properties that it slides very well, low friction, has a bit of resistance, but not too much resistance. So the reason you want a bit of resistance is to suppress the sparking, that it doesn't, because when you take an inductor and you cut the current, you get a huge voltage spike. You understand why? Because there is stored energy in the inductor. When you cut the current, this energy needs to escape. This 1/2 Li squared, okay, is stored in the inductor. When you suddenly disconnect the inductor, where does this energy go? So it has to come out as an electric arc. It's a contact. And that's, so for many reasons, for wear, friction, sparking, the real brushes in a motor are not pieces of metal, but they're a piece of metal, and you connect to it something which is a mixture of carbon and metal powder. So this is typically C plus copper, or C plus silver in better motors. So it's a bit like a ferrite. It's a compressed mixture of carbon powder and metal powder. So the brushes are always made of that, not of pure metal. Okay? So I want to show you, you probably can see the sparking. If I go back and enable the projector, maybe I'll be able to show you the sparking. So this sparking, that was the weakness of the PMDC, or of the commutating motor. Not just PMDC, but all commutating motors. So what's so bad about sparking? Well, I said that was a weakness of this commutating motor. So what's so bad with sparking? Can somebody think of it? Yes?
It oxidizes the contact.
Yeah, it eats up the contacts, because when you see the spark, it means something vaporized typically. Right? The end of the metal vaporized each time just a micron at a time, but it eats up the contact. Also it represents lost energy, because as I said, this energy Li squared becomes a spark, but it's lost energy. So each time you see a spark, there's a bit of loss of energy. Today, it has another big disadvantage, which is the biggest disadvantage today, which didn't exist when the motor was invented. So what's wrong with sparking today?
Fire hazard?
No, it's very little spark. I mean, in a big motor maybe, but there is something which you really wouldn't like if big DC motors were installed near where you live.
Noisy?
Noisy in what way? Acoustic or electrical? Of course, electrical noise, because sparking means it radiates electromagnetic field, because this energy which ends up as a spark, this energy propagates as an electromagnetic field. The early radio transmissions, the transmissions that Marconi did from England to the US, they were just spark generators. The early radio transmitters, all what they were is just sparks, because every spark, basically when Hertz verified Maxwell's theory, all what he did, he made sparks in one end of the room, and he took a metal ring at the other end of the room and saw sparks appearing in the gap. Right, so sparks are actually transmissions of electromagnetic energy. So the classic Hertz experiment was you had a spark gap at one end of the room which made sparks. Then you took a loop of metal and you saw teeny sparks here, which means this loop picked up the radiated electromagnetic waves. So sparks are really transmitters. So today, with everything is wireless, computers, low-level signals, sparks are bad news. Okay, so this is so the three disadvantages of the commutating motor again are wear on the commutator. Okay, wear on the commutator, a bit of loss of energy, and this is not a big factor, but the biggest one today is EM noise. So if you have a very sensitive lab experiment, you don't want DC motors around. Okay, so these are the three reasons why people look for a better idea. Okay, so if that motor has three big disadvantages, how come it's so popular? If you look at your power tools at home, your electric drill, your skill saw, your electric saw, every electric power tool you ever owned has this motor inside, not with a permanent magnet, but actually has this inside with a wound stator, but with a commutator which sparks. Your vacuum cleaner at home has this kind of motor with a commutator which sparks. Your hair dryer has this thing. So basically everything around you has a motor which sparks. Typically this type, not PMDC, but, well, one reason not PMDC because it's running on AC, which I'll talk in a minute. But why is this motor still so popular? Not the PMDC, but the version with the wound field. Yes?
Because it's easy to control.
Easy to control, but there's another. Okay, let me rephrase the question. You can build this motor two flavors, with a wound stator or with a permanent magnet stator. Like the little toys all have permanent magnet stators, but all the power tools, hair dryer, vacuum cleaners, they all have a wound stator. Okay, they don't have a permanent magnet. And why is that? Dirt. I explained it when we talked about actuators. If you have a permanent magnet, you have to have a sealed motor, like a stepper motor. As a permanent magnet, it's sealed. If you don't have a sealed motor, you cannot use permanent magnets because any magnetic particle dirt will stay there forever and eventually fill the gap and jam the motor. So because power tools and vacuum cleaners and all these things have to be made very cheap, you're trying to put in the smallest motor to save money, and then you need to cool it. And the only way you can cool it cheap, if you make lots of holes and you put a fan and air flows through it. But if air flows through it, you cannot use permanent magnets. So because of that, the commutating motor, but not with a permanent magnet, but with a wound armature like this is still the most popular motor in the world. Although it has many problems, but the fact it can be made ventilated and actually force cooled by a fan. Like in a vacuum cleaner, all the suction air of the vacuum cleaner flows through the motor. That's how it's cooled. So the motor can be very tiny and create huge power. Okay, is that clear? Good. So, if I have a PMDC motor and I'll connect it to AC, what will happen? Would it rotate or not? Okay, we can kill. No. Who thinks it will rotate? Okay, so usually most of you don't have an opinion. Okay, so it wouldn't rotate because PMDC means that if you reverse the battery, it will try to rotate the other way. Now AC means 60 times a second it reverses the battery. So first it will try to go this way, then the polarity will reverse, it will try to go this way, it will just vibrate. Okay? Good. In a PMDC. But if I have a motor like this, which is wound field, connected in parallel to the brushes, exactly this, so instead of a magnet I have a coil. If I reverse a battery, what will happen? Pardon?
The magnet reverses?
Yes, so nothing changes. If I take this motor, but B is not created by a permanent magnet, but B is created by a coil. So when I reverse the battery, this reverses, but also the field reverses. So the force stays in the same direction. Is that clear to everybody? So because of that, if the motor is not PMDC, but what's called is a wound field, it can run on AC and DC. And this can only run on DC. Okay? And to show you that it's true, I'll reverse the battery and you see that nothing changed. So, I'll put the motor here, let it run, and then I'll reverse the battery. So let's say here. I know some of you can't see it, but okay, I'll hold it up. So if I make it run, because I want to show you what happens just when I reverse the battery, so we'll do it like this. Okay, so I let it run here. It runs, and just as it's running, I'll reverse the battery. Keeps running the same direction. Now it stopped because, oh, I didn't make contact. Okay, do it again. It's running, you see? And just when it's running, I'm reversing the battery, it keeps running the same direction. So it means it's good. It's good and bad. It's bad that I cannot reverse the direction. But it's good it will run on AC as well. Because a PMDC motor, if I reverse the battery, it will go backwards, which is good for toys, all the little things with PMDC. That's how you do the reversal. Okay? Okay, so is this thing clear? I'm going to go with more detail over it next week, but is it clear to everybody what is a PMDC motor and what's a wound field motor? Okay, so we'll continue next week. I'll bring also more disk drives next week, and some will be left here.